Hey guys, so we're going to do a couple different things here today. We're going to do some percent composition calculations, and then we're going to get into taking percents and converting them into empirical and molecular formulas. All right, we're going to calculate the percent hydrogen and the percent oxygen in some water. So what we do is we use the molar masses to do this. As always, percents are the part of something divided by the whole, and then multiplied by 100. That will give you a percent. So let's say we have 10 boys in a class of a total of 20 students. So we just do this calculation. 10 divided by 20 times 100 is going to be 50%. So we're going to do the same thing with atoms in a molecule. So we're going to do this with the molar masses. So here in our formula, we have 2 hydrogens. So our formula is H2O. So we have 2 hydrogens times the molar mass of hydrogen, which is 1. That gives us 2. And then we're going to take the 1 oxygen times the molar mass of oxygen, get 16. We're going to add these up. So we have a total molar mass of 18. So now to find out the percentage of hydrogen, we do the hydrogen 2 divided by 18 times 100. For this one, we do 16 divided by 18 times 100. Here we're going to get 11%. I'm rounding, and here we're going to get 89%. Okay, so in water, 11% of it is hydrogen and 89% of it is oxygen. You can check yourself easy. You can add up these percents and make sure they come up to 100%. You can be close with these numbers, 99.9. It just depends on how you round it. 100.1, that's fine. But if you add these up and you get something like 105 or 95 or something that's way off, then you did something wrong. So as long as you're close to 100%, you're good. Okay, let's try another one. Let's check out how much magnesium, how much oxygen, and how much hydrogen are in magnesium hydroxide, MgOH2. Let's start off by listing all our elements. We have magnesium, we have oxygen, we have hydrogen. So let's calculate a molar mass. There's only one magnesium there. Magnesium has a molar mass of 24. There's 2 oxygens. Remember, the number outside the parentheses gets distributed to both atoms here. So we have 2 oxygens. Molar mass of oxygen is 16. That adds up to 32. And then there's also 2 hydrogens. Okay, if you don't know how to do molar masses by now, go back to the video that shows you how to do molar masses. You should be an expert in this. Okay, so we're going to add these up. We're going to get 58 is our total molar mass, and molar mass is grams per mole, the unit. All right, so now we're going to do a percentage. We're going to do the part over the whole. So for magnesium, it's going to be 24 is the part, 58 is the whole, times 100. That's going to equal 41.4%. That's the magnesium. Let's do the oxygen. We're going to go 32 divided by 58. We're using these numbers here. Times 100. And that gives us 55.2. And then finally the hydrogen, 2 divided by 58 times 100, part over the whole, and that's going to give us 3.4. So there you go. Very simple calculations. We have 41.4% magnesium, 55.2% oxygen, and 3.4% hydrogen. Add them up just as a check, and this adds up to 100 on the nose. So we did it correctly. This is how the calculation works for this. It's basically the opposite of doing a percent composition. A minute ago, we had a formula and we had to find out the percent of each atoms. Now we're given the percent of each atoms and we have to find a formula. So we're going backwards now. Here's how we do this. You'll be given this information. You have to be given some data. So here we have the percents of some carbon, some hydrogen, and some oxygen. And you're also going to be given a molar mass. So this is how we go about it. We need to figure out how many moles of everything there are. Moles represent ratios of atoms and how they relate to each other. So here's what we're going to do. We're simply going to take these numbers, the 58.8% from carbon, and just turn that into grams. So we're going to make carbon 58.8 grams. And we're going to use the formula that we've been using for a long time now. Grams equals molar mass times moles. This is how we're going to calculate moles. So here's our grams. Again, I just took out the percent sign, turned it into grams. Equals the molar mass of carbon, which is 12, times moles. We're going to do the same thing for the hydrogen. We're going to take the 9.8%, make it 9.8 grams, equals the molar mass of hydrogen times moles. And then finally, oxygen, 31.4% becomes 31.4 grams, equals the molar mass of oxygen times moles. All right, so now we're going to solve for moles over here. So 58.8 divided by 12 comes up to 4.9. 9.8 divided by 1 is 9.8. And 31.4 divided by 16 is... All right, so as I said, these moles, they represent the ratios of how many carbons there are to how many hydrogens there are to how many oxygens there are. If these numbers can be rounded, if all of them can be rounded, and they are close to something that you can round up to or round down to, then just round it. 4.9 easily becomes 5, 9.8 becomes 10, 1.9 becomes 2. You can only do this if all three of these numbers can be rounded and they're very close to a number you can round. If this was 4.8 and this was 9.5, you're not going to be able to do this. But in this case, we can. So this means that our formula is going to be C5, because the carbons have 5 moles, H10O2. This is our empirical formula. This is the lowest whole number ratio. Notice that you can't reduce these numbers. This calculation that we just did gives you empirical formulas. So now we have that. We can take it one step further. We need to check out the molar mass. We're looking for formulas that have a molar mass of 102 in this case. So let's calculate the molar mass of C5H10O2. So this adds up to 102. That matches this 102 over here. So in this case, the molecular formula and the empirical formula are the same formula. If this 102 is a different number, then we'd have to take it one more step, and we'll take a look at that in the next example. Okay, let's take a look at this data. Let's start off by figuring out how many moles we have. So let's do carbon first. Let's make this 50.7 grams. Molar mass of carbon is 12. Hydrogen, let's make this 4.2 grams. Molar mass of hydrogen is 1. And oxygen, 45.1 grams equals the molar mass. Okay, let's calculate, solve for moles here. So here we get 4.2. Here we get 4.2. And here we get 2.8. Okay, we can't round these numbers. Can't just make this 3, 4, and 4. They're too far away to be rounded. So we're going to have to divide by the smallest number that's here. The smallest number is 2.8. So this gets us 1. This gets us 1.5. And this divided by 2.8 is also 1.5. So we're getting a little bit closer. We have at least one whole number. We have 1.5 here. We can't just round these to 1 or 2. We're going to have to take it one more step. So we're going to end up multiplying everything here by 2. Times 2, times 2, times 2. So we're going to end up having our formula be C3H3O2. Empirical. That's our empirical formula. It's the lowest whole number ratio of all the atoms based on their moles. It's all about the moles. All right, so now we have something with a molar mass of 142. Let's calculate this molar mass. We have carbon, 3 of them, times 12. We have 3 hydrogens, times 1. And we have 2 oxygens, times 16. Add these up. That adds up to 71 grams per mole. Okay, so this is our molar mass of the C3H3O2 is 71. So now we take the 142 divided by 71 and we get 2. Again, we get a factor of 2. So now we multiply this 2 by all these atoms here. So it's C6H6O4. This is going to be our molecular compound. The trick here is just getting these into moles that are whole numbers and the lowest whole number ratio of them. That'll give you your empirical formula. And then you take the molar masses of that, you take the molar mass of that and compare it to the molar mass that's given in your problem to get a factor that you can multiply the numbers in your empirical formula to get a molecular formula.